Hi, Simon. Where is everyone? The usual crowd isn't here yet, but hello.
Hey,
Where's everyone? Oh. Oh, Tyler's here. Where's everyone?
everyone's coming in.
There.
How's it going, Tyler?
It's going well. How about yourself?
I don't know. I'm like slightly not feeling well. I forgot that there are other ailments aside from COVID. So yeah,
Oh no.
it'll be okay. So like I said, yeah, it was nice about Alvaro really gave you some good service there. It sounded like you just fixed it right away.
Yeah, he was really quick. It was like an hour after I sent my email, he had a fix already. So
Mhm,
I think he probably had that in mind when he wrote the paper, but somehow wrote that instead.
mhm. Could be. All right. Well, chapter 14 was a bit shorter, so I'm actually, this lecture is going to be really long, I think. So I'm going to cover more of it than I did of chapter 13. So yeah, well, we may as well get started. If you gotta leave early, you gotta leave early, but let's do it. So this lecture is focused on the Brouwer group of a field and its global field, and actually kind of its Delic analog, so sort of second Galois cohomology with coefficients in the Idel group that's closely related to the Brouwer group, as we'll see. Okay. So yeah, so let me just recall, and if we had more time, Brouwer groups are very interesting. Brouwer group of an arbitrary field is an objective interest in pure algebra, apart from its Galois cohomological interpretation. So it'd be nice if we could have spent a little more time on Brouwer groups. But to set this up a little bit, let me recall what we already showed. So for any local field, well, we showed the Brouwer group was isomorphic to Q mod Z, which was kind of a special case, but more following Serre rather than Harari. I guess I showed that for any complete discretely valued field with perfect residue field, the Brouwer group is isomorphic to the Brouwer group of the residue field, direct sum the character group of the field. But in the case of a local field with finite residue field, we didn't just show that the Brouwer group was isomorphic to Q mod Z. We had a canonical isomorphism. And better than that, the isomorphism has very simple functorial behavior. So we have for any local field, there's an invariant isomorphism from the Brouwer group to Q mod Z. But then if you take a finite degree extension, you have a restriction map as usual. And so you can ask, well, therefore, if you go up and over and down, then that gives you an endomorphism of Q mod Z, and you can ask what it is, and it is always just multiplication by the degree. So the way I like to think of this is that this is not just computing the Brouwer group one local field at a time. It's computing kind of the Brouwer functor. So for any local field, and then you have it's also explaining what the homomorphism, what the restriction map is on any finite degree field extension. And in particular, it's computing all of the Brauer kernels. So the Brauer group of L over K for me is the kernel of the restriction map from the Brauer group of K to the Brauer group of L. Well, if the restriction map is multiplication by L over K, evidently its kernel is that which is killed by multiplication by L over K. Okay, so that's it's very, very, very nice if whenever you have a field, understanding the relative Brauer group of a finite degree extension is a very it's very useful thing to know. Okay, so for general K, the Brauer group can be is usually a pretty big infinite torsion group. I guess I would say that for a general field, computing the Brauer group up to isomorphism might not be that hard because it's probably just a really big torsion group. Okay, and so a big torsion commutative group doesn't have the most complicated. There's not that many possibilities as to what the structure could be, and so in general, it's probably just really big. But if you want to compute it compatibly with restriction in the above sense, that's much more difficult. Okay, so if you could do this for a class of fields, like that's really pretty exciting thing to do, sort of in Brauer group land. So while we're in Brauer group land, just for a moment, what are some other basic properties to ask about elements of the Brauer group? So again, I didn't emphasize this too much in this course, but the elements of the Brauer group of a field parameterize isomorphism classes of division algebras over the field that are finite dimensional over K and have center exactly K and no larger. Okay, so that's one interpretation of elements of the Brauer group. And so every element of the Brauer group gives you a K-central division algebra. And so there are questions that you can ask about division algebras. One question is every division algebra split by some cyclic extension? Okay, so again, same here it's just about this question. I didn't need to represent it by a division algebra. I could have just asked, is every element of the Brauer group killed by restriction to some cyclic extension? Okay, a priori, it's killed under restriction to some separable extension, therefore to some Galois extension, but that's all that you can say just kind of by general nonsense. But actually, it's more natural to ask a stronger question. You'd like to know whether it's split by a cyclic extension of the right degree, of the degree equal to the degree of the division algebra. What's the degree of a division algebra? The degree of a division is measuring just the dimension over K, but because when you extend scalars to the algebraic closure, it's going to become a matrix algebra. The dimension has to be a perfect square. So it's more natural to say that the degree of a division algebra is the square root of the dimension. Okay. This is also the index in the cohomological sense. It turns out you can say it more Galois cohomologically, but the index of a Brauer class is in fact equal to the degree of its division algebra. So for instance, quaternion algebra is synonymous with division algebra of degree 2. Okay, and so yeah, if so, if division algebras that are split by cyclic extensions, this is the minimal possible degree of a cyclic of any field extension that could possibly split division algebra, and so that's equivalent to, in fact, that's equivalent to L embedding inside the division algebra as a subfield. Okay, and so such things we call cyclic algebras, and cyclic algebras are sort of the nice class of division algebras. In my summer half course on non-commutative algebra, I ended with a brief discussion of cyclic algebras, so you could see chapter 8 of, or whatever, section 8 of my notes, or you could open a whole book on division algebras, like Pierce's graduate text, Associative Algebras, is highly recommended. Yeah, so one basic question, just to give you a sense of how tricky these things can get. So it is an open question since I think the 50s, whether every division algebra of prime degree is necessarily cyclic. So every quaternion algebra is split by a separable quadratic extension. So division algebras of degree 2 are cyclic. Division algebras of degree 3 are also known to be cyclic. I don't remember why. And I think it's already open as to whether every division algebra of degree 5 has a cyclic subextension of cyclic Galois subextension of degree 5. And so in general, algebras don't need to be cyclic if in general applies to the field as well. So a sort of example, I think this works. I didn't go back to check this, but I'm pretty sure. So we can define these Hilbert symbols or norm residue symbols. We defined those before. Whenever you have a primitive n-through unity in the ground field, I gave you a sort of cohomological description. You could also define them just as algebras. And so if I take my field to be the complex number, so I have all the roots of unity I want, and then I have 4 independent indeterminates, so rational function field in 4 variables over the complex numbers. If I just take sort of, this is like a generic Hilbert symbol, so the A and B are independent indeterminates, and then I take the tensor product with another generic in itself, and anyway, so there's just absolutely no relations here, and so I'm pretty sure that it is true and sort of standard to prove that. So this algebra has period n, okay, because in the Brouwer group, each one of these elements is n torsion, and this tensor product corresponds to the sum in the Brouwer group. So these guys are going to have period n and index n squared, and I'm pretty darn sure that they do not have a cyclic splitting. Okay. Yeah. And so again, just yeah. So for an element in the Brouwer group, you can define the period. You can define the period in the index of any Galois cohomology class, and so that has a nice description on the division algebra side as well. But you can just define it using Galois cohomology. I think I did this last year around this time. So the period, so the Brouwer group is H2 Galois cohomology with coefficients in the multiplicative group. So it's certainly a torsion group. So the period is just the order. On the division algebra side, the period is the smallest number of times that you tensor your division algebra with itself and get a matrix algebra. And then the index is the GCD of all degrees of finite splitting fields of the class. And I said on the division algebra side, the index is actually equal to the degree. Okay. Let's see. So yeah, so as an exercise, if you want any more exercises, when the field is local, this functorial description of the Brouwer group of K, which I just recalled on the last page, you can use this pretty easily to show that every division algebra over K is cyclic, meaning it has a cyclic splitting field of degree equal to the degree of the algebra and has period equals index. Okay. And then recall, by the way, that just the fact that restriction followed by co-restriction is multiplication by the field extension, this immediately implies that the period divides the index for any Galois cohomology class whatsoever. Okay. Right. So basically, this is showing you that what is it? Every class in the Brouwer group of a local field, every class of order n is split by an extension of degree n, and that's period equals index, and then whatever that extension is can be taken to be cyclic. Okay. So now I want to study the Brouwer group of K, where K is a global field. And so as written, just as in the local case, it has an important role to play in class field theory, but also the Brouwer group of a global field is an important and interesting object in its own right. Oh yeah, I will say this. So yeah, so for instance, over any field, the Brouwer group of K also parameterizes Savary-Brouwer varieties. So what are these? These are nice varieties over K that when you extend scalars to even the separable algebraic closure, they just become projective space. Okay. So the Brouwer group of K is telling you about certain very, very nice kinds of varieties without rational points. And as a special case of this correspondence, you get a bijective correspondence between quaternion algebras over any field whatsoever up to isomorphism, and genus zero curves over any field up to isomorphism. So all I'm saying is it's pretty clear that an arithmetic geometer who's interested in rational points would be interested in the Brouwer group, and then Of course, there's, I shouldn't say of course, but there's this thing, the Brouwer-Mannion obstruction, which is a very, very deep relationship between, it's a very, very clever way of using Brouwer groups to study local global problems for varieties over global fields. Okay. Not that that's what I'm going to talk about. So, all right. So it turns out that the Brouwer group of a global field has kind of the nice properties that I just pointed out. I won't quite come back and prove it, but it is true that every division algebra over a global field is also cyclic. Okay, so again, is split by a cyclic extension of degree equal to the square root of the dimension of the division algebra, which equivalently means that inside the division algebra you can find a cyclic degree. If your division algebra has dimension n squared, then it contains a cyclic subfield of dimension n. Also, the period is equal to the index. Okay. Right. Okay, and we will get our computation. In fact, we're going to compute the Brouwer group of a global field by relating it to the Brouwer group of all of its completions, which is a good thing to do because we have such a perfect understanding of the functor of a functorial understanding of the Brouwer group of a local field. And so if we can compute the Brouwer group in particular, we'll find that the Brouwer group of a global field injects into the direct sum of the Brouwer groups of all of the completions. And even that fact is already kind of solving the splitting problem, because therefore to split your Brouwer group element globally, it suffices to split it everywhere locally. Okay, so let's get started with so until further notice, K is going to be a global field. Okay, so let's see. I might have skipped this, but all right, I guess I'll do it. So if I have a prime number and I have an infinite degree Galois extension, okay, so I don't mean it's allowed to be infinite, I mean for once that it has to be infinite. If p equals 2, we assume it has no real place, so we'll see why in the proof. And then suppose that for every place, remember that I've chosen a place of k sep lying over for every, what am I trying to say? I'm trying to say that I've embedded the algebraic closure of k sep into the algebraic closure of kv, and so therefore for every algebraic extension of k, that determines an extension of a place v. So I call that v bullet. And as long as the extension is Galois, it doesn't matter. They're all isomorphic as kv algebras anyway. So for all places, I want to assume that the corresponding completion has a degree divisible by p to the infinity. Okay, so what in the profinite set? So what does that mean? It means that for all n, there's a finite degree subextension of degree divisible by p to the n. Okay, and so then let's see. So this IL is just the Adel group of this infinite degree Galois extension. So what else could that be but the direct limit of the Adel groups over the finite extensions? What's the result? The result is that the p primary torsion, if it's such a big extension so that even locally its degree is infinitely divisible by p, then that's big enough to kill the p primary component of this group, which by the way is essentially some kind of direct sum of Brouwer groups. And so this is basically saying that after we make a large algebraic extension, some Brouwer group is going to be equal to 0. That's what it's getting at. So this one is equal to 0, and therefore if you go from k up to L, so that relative Brouwer group captures the absolute Brouwer group. And then this last thing is just coming from some short exact sequence. So okay, for whatever it's worth, I will do the proof just to show you that there's nothing too bad is happening here. So what's the proof? So we know one of the main things we proved in chapter 13 is that Galois cohomology of the Adel group was equal to 0. Okay. Yes, that's true. So this, basically, I mean, it's because this thing is the direct, we prove that the Galois cohomology, the Adele group, is just the direct sum of the Galois cohomologies, the completions, and then we just apply Hilbert 90. Okay, so that's 0, and then the inflation restriction sequence gives us a little bit more because some of the other ones were equal to 0, and so then we get relative second cohomology goes into H2 of K, goes into H2 of L, and so if I can show that the p primary torsion is 0 here, which is one of the things I said, then it certainly follows that this map induces an isomorphism on the p primary torsion, which is the other thing that I said. Okay, and so again, yeah, so the Galois cohomology with coefficients in the Adele group really just breaks apart as the direct sum of local Galois cohomology groups. Okay. So what's the point? The point is most of the action, as usual, is happening at the non-Archimedean places. So if we're non-Archimedean, remember that LV itself is already an enormous infinite degree extension of KV, so enormous that it has sub-extensions of finite degree divisible by every power of p. First of all, as usual, but first of all, like any infinite degree Galois extension, it's defined as a direct limit of finite Galois extension. So every element of this lives in a finite degree extension. So an element of this is in a really big infinite degree extension. It starts out actually by definition in some finite degree extension, and then there's an infinite, there's like a p to the infinity amount of restriction going on. That's basically by hypothesis. But this guy is the Brouwer group of this algebraic extension of KV, and so so I start with an element of the Brouwer group of a finite extension, so also the Brouwer group of a local field, and then I restrict p to the infinite times. Well, that's going to multiply the degree by p to the infinity, or multiply it by p to the n for as large an n as you please, and therefore it will kill any p primary torsion element. Okay, so what about if it's Archimedean? Well, if it's a complex place, then everything is just trivial. The Brouwer group of the complex numbers. If V is complex, then KV and LV both have to be the complex numbers, and nothing's going on. What if V is real? Then the Brouwer group here is going to, let's see. I guess there's a couple choices here. So this, if V is real, let me think for a second. If V is real, then so then LV is either going to be the Brouwer group of R or the Brouwer group of C, right? If it's the Brouwer group of C, it's trivial, that's fine. If it's the Brouwer group of R, which could only happen if I had real places, well, what did I assume? I assumed that if I had any real places if I have real places, I need P to be odd. So okay, I'm just assuming that the one group that could be non-trivial here. So this is the P to the infinity torsion in either the Brouwer group of R or the Brouwer group of C. But if it is the Brouwer group of R, I'm not allowed to have P equals 2, but the Brouwer group of R has order 2. Okay. So there's kind of nothing going on here. The hypotheses are precisely so as to make sure that the Archimedean Brouwer groups are all 0, have no p primary torsion. Okay, so that's the end of that one. So now, well, what is an example of this kind of really big algebraic extension whose local degree is going to be divisible by p to the infinity? Okay, in fact, cyclotomic extensions will give you good examples. So like I said, as for any field, I can take the cyclotomic extension, which means just to join all roots of unity in a separable closure. It's definitely an abelian extension with Galois group, a subgroup of Z hat cross. Right? In characteristic P, this is a very nice extension. The maximal cyclotomic extension. Well, it's a very simple extension. Okay, it's maybe too simple to be interesting as what happens in the number field case, but it will still serve our purposes here. In the function field case, to adjoin roots of unity, well, you're just adjoining roots of unity from the ground field. You could say it that way. And so therefore, the automorphism group of K-sec over K is, I mean, I took a regular function field over FQ and made a Galois extension. So the Galois group is just the Galois group of the field extension, which is Z hat. And then again, in the function field case, K-sec over K is everywhere unramified, right? So that's what's definitely not happening in the number field case. Okay, so in the number field case, I also want to look at the p cyclotomic extension. Okay, there's only one thing that could mean. I adjoin p power roots of unity. Then if I look at so by GP will be the automorphism group of the p cyclotomic extension. Okay, so now it's the p cyclotomic character gives you a homomorphism into ZP star. So what you would learn, just the irreducibility of cyclotomic polynomials over Q tells you that this map is surjective as well when the number field is Q, and so therefore this cyclotomic character is obtained by taking a surjective cyclotomic character and restricting to a finite index subgroup. So therefore its image is gonna be open. In particular, a finite index in ZP star. Okay, and so then what am I doing? Basically, I'm building the cyclotomic ZP extension of my number field. That's what's happening here. So okay, so it's an open subgroup of ZP star where we had a discussion of open subgroups of the unit group of a p-adic field. Every open subgroup, what am I trying to say? Is isomorphic to the additive group of the p-adic field direct sum, possibly a finite torsion subgroup. So if I mod out by the torsion subgroup, then I do get ZP. And okay, well, therefore, just Galois theoretically, that does give me a ZP extension. So K tilde of P, so I take K-sec, just do doing it quickly, but the Galois theory works out. If I do K-sec and I mod out by GP tors, then the automorphism group there is going to be gamma P. And so that's a cyclotomic. That by definition, this is the cyclotomic ZP extension. So every number field for every prime P admits at least one ZP extension. This is the easiest one. Okay. That is not the right definition. K should be the product over P. K tilde should be the product over P of K tilde P. Okay. So the next result here is for any non-Archimedean place, the decomposition group of this product of cyclotomic ZP extensions is isomorphic to Z hat. There's a little bit of a beware, like no, I guess, well, it's this thing, what am I trying to say? Wait for a second. Okay, so I mean, the global group itself is going to be kind of equal to Z hat because each one of these is a ZP extension, and certainly any two ZP extensions will be disjoint from each other. They have coprime orders, and so I think what's happening is that the automorphism group of K tilde over K is Z hat on the nose, and now I pass to a decomposition group, but I'm not saying it's the whole global Z hat. I'm saying it's isomorphic to Z hat. Okay, this is not really going to come up though in what goes on, so not something that we need to worry about too much. Okay, so here's the next key proposition, which is doing much of the work and giving us cyclic splitting fields for the Brouwer group. So yeah, so it turns out that second Galois cohomology, the Adel class group, again, this will turn out to be very close to the Brouwer group of the global field. So it is, but by definition, it's the direct limit over all finite Galois extensions. But so the assertion is that it's also the direct limit over finite cyclic extensions. You can actually say a little stronger. If K has no real places, you can actually get cyclotomic splitting fields. So you can take your cyclic extension inside this this group K cross, okay? And now I realize that I wrote cyclic here, but I don't need to, because the Galois group of K tilde over K is Z hat. So every finite sub-extension is cyclic. And then if K has no real places, you just have to do something once. It's almost true. You take any imaginary quadratic extension of K, and then the same holds. You're going to get a sub-extension of K1 tilde. Every splitting field can be taken there. And then if you take your imaginary quadratic field just to be K joined square root minus 1, that's cyclotomic as well. And so it follows that even when there are real places, every element of this second Galois cohomology group is split by a cyclic cyclotomic extension. Okay. All right. And so, yeah, the next result is, as promised, we deduce from this that every element of the Brouwer group of a global field has a cyclic splitting field. Okay. And how do we deduce this? Well, we have this commutative diagram where the rows and columns are exact. Okay, what's going on? Where is this coming from? Here we're taking Galois cohomology of what? LSEP cross into a Adel class group into LSEP cross into Adel group into Adel class group, but the first Galois cohomology of the Adel class group is equal to 1. That was one of the main things that we proved before, and so therefore that's why there's a 0 there. Similarly here, okay. Let's see, maybe we did what I just said and then we passed to the limit over. No, never mind. So sorry. So let me think for a second. Right. So here we're taking L over K is going to be a cyclic Galois extension. Okay. And so we have this kind of setup. And so what's the point? The point is up here. We said that every element of H2 with coefficients in the Adels is split by a finite cyclic extension. So take your element, and I'm getting that the Brouwer group of K is injecting inside of H2 with coefficients in the Adels. So take your Brouwer group, map it inside here, and then choose a finite cyclic extension that splits this guy by this proposition. And then this commutative diagram says, all right, well, you know, if I go up and I go over, then I get 0 because I rigged things to get 0 when I went over and up, okay? And so whatever this map is, it maps to 0 in here, but this map is injective, so this element was already 0. Okay, so again, the fact that every element of the Brouwer group has a cyclic splitting field follows pretty easily at this point from the fact that every element of the, you know, Adelic analog of the Brouwer group has a cyclic splitting field. Okay, and again, I just want to remind you, this is not what we mean when we say that every element of the Brouwer group is a cyclic extension. It's weaker than that. Sorry, is a cyclic algebra. To be a cyclic algebra, it should have a cyclic splitting field of the smallest possible degree. Okay. But that's progress. All right, so now we are ready to define the global invariant map. Okay, so I think for most of L is always going to be a finite Galois extension. You just have to check to see whether it's, and G is going to be the Galois group. You just have to check whether it's cyclic or not. Okay, and so at the moment, I take any finite G Galois extension. GV is the decomposition. This is the automorphism group of the completion at the distinguished place, which we also realize as the decomposition group. So this is canonically living as a subgroup of the global Galois group G. Okay, so I'm going to define a global invariant map. Okay, whereas the local invariant map went from the Brouwer group into Q mod Z, this one is going from kind of the Adelic version of the Brouwer group. But again, we're going to see in a second that that the Brouwer group sits, the global Brouwer group sits inside this. Okay, so we have our invariant map from H2 with Galois cohomology in the upstairs Adel group, and kind of as expected, it lives in the the degree of L over K torsion subgroup of Q mod Z. Okay. So that's the map that I want to define, this sort of global invariant map. How do I define it? I define it as the direct sum of the local invariant maps. So if, again, remember, I didn't prove this, but we stated it last time again, that the Galois cohomology, the Adel group, just splits up as the direct sum of all the local Galois cohomologies. So an element in here is literally just a direct sum of elements of, what are these? These are just sort of relative Brouwer groups. So these are elements. Each one of these is the Brouwer group of LV over KV, which is sitting inside the Brouwer group of KV. Okay. And so therefore we have an invariant map defined from the Brouwer group of KV into Q mod Z. And so I just take, what luck. I have finitely many things that are landing in Q mod Z. And so I should map the direct sum of them to the sum of the invariant maps. Okay, so that's just kind of, if you get to this point, this is a very obvious thing to do. All right, a couple checkups though. I told you what it was implicitly here. I was thinking, so this is the invariant map that we defined before for any local field. But again, there's a little bit of trouble at the Archimedean places, right? If you complete a number field in the Archimedean place, you get something which some would call a local field, but it's not the discretely valued field that we were working with before. So what are we doing at the Archimedean places? Let's see. So first of all, this should be right. So I need something on the relative Brouwer group. So if you think about it, there's kind of only one non-trivial case. Each one of LV and KV is either R or C in the Archimedean case. Well, the Brouwer group of C over C should be 0, and the Brouwer group of R over R should be 0. The elements of the Brouwer group that are already split are 0. So the only interesting case is if V is real, but its canonical extension is complex, in which case I get the relative Brouwer group of C over R, otherwise known as the Brouwer group of R. And now what am I trying to do? I'm trying to give you a map from Brouwer group of R into Q mod Z. Well, if you think about it, the Brouwer group of R has a group. It's a group of 2 elements, and so you tell me where the non-trivial element of order 2 of the Brouwer group goes. It either goes to 0 or it goes to the unique element of order 2 in this group, right? And well, guess which one is right? The non-trivial one is right. So so it's just the unique isomorphism from this group of order 2 to this group of order 2. All right. Okay, so that's the real places are doing something, the complex places are doing nothing. All right, and so just again as a little checkup here, for every non-Archimedean place, remember we've also defined a reciprocity map. That was where a lot of the Tate Nakayama stuff was being, so this reciprocity map was the inverse of some cup product isomorphism that came from the Tate Nakayama theorem. Okay. Anyway, but of course we have such a map. Okay. Not only do we have a map, we know that it's surjective with kernel equal to the norms from up. Okay, so again, what should the local reciprocity map be in the Archimedean situation? Okay, so kind of same deal. If it's C over C or R over R, nothing can come of nothing, so that should be trivial. And so the real case is what should the map be from what should the map be defined on R star? Okay. Well, now I want to map from R star into the automorphism group of C over R, which is another 2-element group whose non-trivial element doesn't really matter, but of course it's complex conjugation. And so, well, okay, here you may have to think a little bit, but I want this, presumably I want this to be an isomorphism with kernel equal to the norm map from C. right? Just to make things work the same way as they did in the non-Archimedean case. Which elements of real numbers are norms from the complex numbers? They're precisely the positive real numbers, okay? And so therefore the map should probably just, basically what am I doing? Basically this map is modding out by the identity component of this topological group, okay? So it's taking, that's a fancy way of saying it takes positive elements to one, it takes negative elements to complex conjugation, and therefore it induces an isomorphism on the norm co-kernel. Okay, so that's what these things are. And then if you really think about it, so I've defined a, just a global map. In the local case, I have to compile everything, and it had to prove that these reciprocity maps for the these relative extensions compiled correctly, and therefore they compiled into one map with domain KV star. Well, here I'm already telling you what the one map is. That's take a positive real number to the identity, take a negative real number to not the identity. Okay, so those are what the local reciprocity maps are. And so now I'm ready to define the global reciprocity map. So again, for any G-Galois extension L over K, what's going on here? So the global reciprocity map is going to be a map from the Adel group into the abelionized Galois group. Okay, the case of interest to us is where the map is also abelian. And so if you sort of think about it, what's going on? An Adel is a restricted direct product of local guys. And so for each local guy, I can just plug it right in. I can plug it right into the local reciprocity map, right? And what kind of sense does this make? Can I take the product? Well, there's a couple of things to worry about. First of all, the image of the local reciprocity map is landing inside the abelionization of GV. That's not a problem because, again, GV can be viewed as the decomposition group. So it's a subgroup of G. And okay, whenever you have a homomorphism of groups, there's an induced homomorphism. You mod out by the commutator subgroups, and you get an induced homomorphism on the abelionization. I don't claim that's an injection, unless the groups were already abelian, which is the case that we really care about, in which case it obviously is. Okay, and so that's what's happening. And so therefore, it does make sense to take, to start multiplying together these images of these reciprocity maps, but there's something else to show, right? Because here I have an infinite direct product, which is just landing in a finite commutative group, right? So I can't, what kind of actual infinite product could I possibly have taking values in the finite commutative group? I better believe that for each fixed alpha and all but finitely many v, this thing is 1. So it's not actually infinite. And sure, we can see that. Why is that? Well, if you take the place to be non-Archimedean, which is all but finitely many, and you take it to be unramified in your finite degree Galois extension, which is all but finitely many, and you take it to be a local unit at V, which is all but finitely many by definition of the Adel group, well then, as we proved, every unit is a norm from an unramified extension, right? So the image of the unramified extension, remember, the image of the norm map was precisely all elements whose valuation is divisible by the degree of the extension. Norms have valuation 0. 0 is divisible by the degree of the extension. Okay. So yeah, in an unramified extension, as we've certainly seen before several times, all the units are norms. Great. So that already that explains why all but finitely many of these components are equal to 1. So get a drink here. Okay. So yeah, and so the product is only formally infinite, and it makes sense, and we get a globally defined reciprocity map. Okay. And so then the next result, which I'm not really going to talk about, but I think it does follow pretty quickly from the completely analogous result in the local case, which so we have a finite G-Galois extension. It's really saying that there's a compatibility between the reciprocity map and the invariant map. So if I have a character on G, then again, you know, just taking the standard Galois cohomology of Z to Q mod Z, then I can take the what you call it, the coboundary of the character is gonna be an H2G with Z coefficients. And so if I can take the cup product with an element, with an Adel, which is an H0 of the Adels in the finite extension, and that cup product is gonna land where? It's gonna land in H2 with coefficients in the Adels. Great, that's where my invariant map is defined. Okay, so this makes sense. And then on the left-hand side, I'm getting an element of the abelianization of the Galois group, and that's exactly what this character is exactly giving me a homomorphism from that to Q mod Z. Okay, and so again, the point is that we've seen literally this exact result in the case of a local field, and these maps are essentially defined as component by component their corresponding local things, so it's not surprising that this is true. Okay, and then there are some compatibilities, just as in the local case. So there are some compatibilities when you go from one larger finite degree extension down to a smaller finite degree extension, sort of as we were talking about. And then there's some co-restriction compatibilities, which I've written down here. But again, they're kind of exactly the same. So here, if I do restriction on what really looks like the adelic version of the global Brouwer group, then restriction in a certain degree extension is really just multiplication by the degree of the extension. Sounds great. Co-restriction induces an injection. Okay, well, again, this is the same as what we said in the local case, and it is true essentially because it is true in the local case. Okay, so now we pass to the limit over finite Galois extensions, and then we get our invariant map, right? So before, remember, the invariant map was defined for a finite Galois extension with coefficients in really the degree of the Galois extension torsion subgroup of Q mod Z, and I just pass to the limit, and I get my global invariant map, right? Okay. Right, and this is the map which in the local case would be, in the local case, this would just be the Brouwer group, and this would be an isomorphism. So what's the question is like, what's happening in the global case? All right, so that's what's happening in the global case is coming up soon. But first, we have this very important global reciprocity law. So by the way, a lot of the proofs that I've skipped here are actually pretty routine, like not even the one that I did was not the easiest, you know, necessarily, but a lot of the action is here. So I feel bad about skipping this. Here there's something to do. Okay. So if you take a finite abelian extension now, then the first thing is that if I go from this is the literal relative Brouwer group, okay, Brouwer group of L over K goes into its adelic analog, followed by this global invariant map. So the composite here, the composition is trivial. Okay, that kind of sounds like a reciprocity law. Okay, that's what's coming. And then what's the correspondent? Well, what else are we saying? What are we saying on the? This is on the invariant map side. What are we saying on the reciprocity map side? We're saying again, the reciprocity map is a map. Remember, defined on, where did it go? Yeah, the reciprocity map was defined on, did I not pass to the limit on that too? Did I miss it? Where did I do that? I think I meant to. So here at the moment, this reciprocity map is being defined on finite Galois extensions, but all right, I guess I can write it down here. If you just pass to the limit over finite Galois L over K, well, then if you pass to the limit, you're going to get so you're going to get an actual reciprocity map. Okay. I guess that's not what's happening right now, though. Okay, whatever. Maybe I didn't need to say that. Yeah. So at the moment, I'm sure that happens later. I guess we just don't need to say it yet. Okay. So the global reciprocity law, we're still looking at this kind of finite level reciprocity map, which again, the overall reciprocity map is just going to be obtained by passing to the limit. Never mind. I don't think we need to do it. Okay. So right. So at this finite level, the reciprocity map applied to a principal Adele, namely the things that are actually being diagonally embedded from the global field, is equal to 1. And therefore, we get something that we've been waiting to hear for quite some time. Therefore, we have a reciprocity map that factors through the Adele class group. Okay. So this is very exciting for us, right? Because now if I pass to the limit, right? I pass to the limit kind of, I have to check compatibility, but compatibility is probably something that I already said that we had anyway. So once you establish that when you go from a bigger Galois extension to a smaller Galois extension, you get, I think maybe that's part of what I meant when I said this, so that this reciprocity map is compatible upon restriction to a smaller Galois extension in just the same way that we already wrote it down for the case of local fields. And so therefore you pass to the limit, and this reciprocity map is giving us a homomorphism from the Adele class groups of K into the abelian Galois group of K. Hey, that's what class field theory is supposed to be giving us, right? So this is going to be the fundamental reciprocity homomorphism, which is supposed to be an isomorphism on the profinite completion, blah, blah, blah. All right, so corollary, if we have a finite cyclic G Galois extension, then we have this nice short exact sequence. Okay. So the short exact sequence is comparing the actual global relative Brouwer group to its Adelic version. Okay. And so what's the difference? You see that the global Brouwer group sits inside the Adelic Brouwer group, but it's not the whole thing. It's pretty close. I mean, by the way, so this, in the local case, this was still a finite group. In the global case, this is actually an infinite group as long as G is trivial. Wait, is that true? Hold on. Wait, did I say something wrong? Let me think. Of course, what I said is true, because since it's a cyclic group, this is isomorphic to Tate H0, which is the norm cokernel, and the norm cokernel is really big for an extension of global fields, as we said. Yeah. So even if G is a quadratic extension, this is if L over K is a quadratic extension, this is already an enormous infinite group. Okay. So that's kind of helpful. What I'm saying is that, so this group is actually infinite, and so it sits inside this infinite group, and therefore it's really only slightly smaller because the quotient is finite. Okay. All right, and I think I will prove this. So step 1, we deal with the case that's not just cyclic, but cyclic of prime power. And then the claim is, if you have a cyclic extension of number fields of prime power, then there's going to be a place for which the entire Galois group is the decomposition group of that place. And I hope that many of you know that this is a special case of the Chebotarev density theorem. Okay, so the Chebotarev density theorem says, it says lots of things, but so it says that for an abelian extension, it says that every element in the Galois group is going to be the Frobenius element for infinitely many places, right? And already that would be enough. In fact, that would, let me think about it for a second. Yeah, I mean, that would tell us, that would give us the answer for any cyclic extension, not just cyclic of prime degree. So in particular, Chebotarev density says if you take any cyclic Galois extension, then you take a generator of this cyclic group, and that one automorphism will be the Frobenius automorphism for infinitely many places. So this is a special case, very special case of Chebotarev density. The point, though, is that Harari proves the special case of Chebotarev density in chapter 13. I mean, the proof of Chebotarev density has something to do with class field theory. I don't think it's circular. Anyway, but it can only help to know that this particular special case of Chebotarev density is proven in an elementary way earlier. Okay. Anyway, so what does that mean? Well, that means that if you just look at the component at V of this invariant map, well, the local component, we know everything there is to know about the local invariant. The local invariant map is going to be an isomorphism from the Brouwer group onto this cyclic group of that order. And so what we already know, in this case, already just looking at the V component tells us that the map is surjective. Okay. I mean, in general, the V component would be surjective onto 1 over LV divided by KV, but if there's an inert place, then that local degree is equal to the entire degree. Okay. Yeah. And so what about the general case for the surjectivity? Well, that just follows from these functorialities that I was waving at above. So if you think, so if I have an arbitrary cyclic group, you break it up into its CeLO P subgroups, which are cyclic of prime power order. I won't do it, but if you just, I think maybe I'll just leave it there. You break things up into the CeLO P subgroups, and you use the fact that you restrict to the CeLO, whatever. I won't do it. It follows pretty easily from the prime power case again. Or just to be clear about it, we could just use the less special case of Chebotarev density, which would tell us that the entire cyclic group is equal to GV for infinitely many places. Okay. All right. So now step 2, we know that first Galois cohomology of the class group is equal to, Idel class group is equal to 0. We certainly by Hilbert 90 know that we proved that before. I don't think we proved it, but it occurred on a page in chapter 13. And then this is just Hilbert 90. Since the group is cyclic, if H1 is 0, then so is every odd H. So H3 is also 0. Okay, and so then if I just take my Galois cohomology of my Idel group, principal Idels into Idel classes, the H1 with coefficients in CL was 0. That's why that's 0. We get an alpha here, and then the next one would be H3 with coefficients in L cross, which is 0. So we certainly get the short exact sequence, which tells us that this guy is built up out of these two pieces. Okay, so for one thing, that tells us that this map alpha here. So it's a little bit funny. I'm trying to prove that this sequence is short exact. The first two terms and the map are the same, but then here I have some, something else. And then over here, I have something else. But again, notice that the first two terms and the map are exactly the same. So that certainly also proves that the map is injective because it's the same map. And so where are we now? Now, if you go back here, what have we proved so far? We've proved that this map is surjective. That was the first thing we did. And then we proved that this map is injective. Let's see. We also know, okay. So we know that the co-kernel of alpha is equal to, well, the size of this. That's the way short exact sequences work. And again, it's cyclic, so that's the same as Tate H0. And this was, we worked on this. This was the, or somebody did, this was the class field axiom that the Tate H0 of the Adel class group, just like in the local case, is the degree of the extension. Okay, so therefore this piece kind of has the same size as the piece did in the exact sequence we want. They both have size equal to the degree of the extension. The global reciprocity law, which was our previous result. Let's wait, hold on. Sorry, so the global, so here I've just repeated this sequence that I'm trying to show is exact. Again, I know this is surjective. I know this is injective. The next thing I want to show is that if I do 2 steps, I get 0. That's why it's a complex. And that really was exactly one part of the global reciprocity law. The global reciprocity law said, if you take the invariant of a principal Adel, then you get 0. Yes, that was exactly what part of the global reciprocity law said. All right, and so we're a little raggedy about it, but we're basically done. And so what's the point? So now I know this one is injective. I know this one is surjective. I know the composite is equal to 0. And so, yeah, so what am I worried about now? So I can take this guy, modulo this guy, and I map it into that guy. So okay, so I have this map from the quotient in there, and I'm trying to show, I know that this map is surjective, and I'm trying to show that it's an isomorphism, but both of these are finite groups of size the degree of L over K. That one is visibly has size degree L over K, and this one, as I just said, using the other exact sequence, the size of this quotient is the same as the size of this guy, which by the class field axiom did have degree L over K. So no problem really. It follows the exactness of this sequence follows easily from the other stuff. Okay, so what did we just prove? We just proved this exact sequence. Okay. And now we're ready to put everything together because on the one hand, we proved this for finite cyclic extensions, but on the other hand, we proved that the entire Brouwer group and its Adelic analog are direct limits of cyclic extensions. So if I just take the direct limit over all of these, I'm going to get an enormous theorem. So that Albert, Brouwer, Hasse, Noether theorem. Harari leaves out Albert, who's the only American mathematician in here. But anyway, I think it's usually, often people put Albert in there. So if you have a global field, then you have a short exact sequence. The Brouwer group of the global field injects into the direct sum of the local Brouwer groups, okay? And again, most of these places are copies of Q mod Z, right? But if there are real places, there are 1 over 2 Z mod Z. So there could be finitely many extra order 2 groups. And then we have this, invariant map, okay? So each one of these is isomorphic to Q mod Z, so it makes sense to add up an element of the direct sum. And so this is our exact sequence. And again, what this is saying is that first of all, the Brouwer group, the global Brouwer group injects into the direct sum of the local Brouwer groups. Even this injection would be called the Hasse principle for the Brouwer group. Okay. So in other words, if I have a division algebra, if it's a matrix algebra after you base change to every completion, then it was already a matrix algebra. That's one way of saying it. Another way of saying it, on more geometric way of saying it, Brouwer group elements are parameterized by Savary-Brouwer varieties. So if I have a Savary-Brouwer, something which is geometrically isomorphic to projective space if it has a rational point. Oh, by the way, it's a very Bauer variety is isomorphic to projective space over the ground field if and only if it has a rational point. So if your twisted form of projective space has a rational point over every completion, then it already has a rational point. So that's really the Hasse principle. Okay, so it is literally a local global principle for a class of varieties, namely twisted forms of projective space. Okay, and then this part is very exciting as well because it's saying that the global Brouwer group, again, this group is really big. This group is the direct sum of infinitely many copies of Q mod Z, okay? And this one is only one copy of Q mod Z. So evidently this group is much bigger. And so this group is really almost as large as this one as well. But there's this one little correction factor in the fact that you have this, the fact that you don't just have 0 here, but you have this one constraint, which is that the sum of the invariants should be equal to 0, is also very exciting. Okay, so the proof of this is no problem. Using the previous results, what were propositions 14.4 and 14.5? Yeah, so 14.4 and 14.5 told us that the Adel class group was the direct limit, not over all Galois extensions as it was defined, but over all cyclic extensions. Similarly, the Brouwer group was the direct limit over cyclic extensions. So, okay, so like I said, you take the exact sequence that we just established for every finite cyclic extension, pass to the direct limit. By what we just proved, this direct limit is actually the entire Brouwer group of K. And by what we just proved as well, this direct limit is actually the entire Adelic analog. Okay. This is the same Q mod Z. Okay, so that's the that is almost the proof. I guess the last thing is to explain why is this thing equal to the direct sum of the local Brouwer groups, but that's pretty clear too. Yeah, so this map from H2 is obtained by identifying, again, we've used this a couple times, Galois homology in the Adel group really just splits up as the direct sum of the Galois homologies on the completions. And so this just gives us literally does give us the direct sum of the local Galois groups. And then that was 13.1. And yeah, so what is the map? The map is just the sum of the local invariants, which was our definition of the global invariant. If we go back. Yeah, so we did define a map from, we did define it at the finite level, and then we passed to the limit, which is what we just did. But what after all is this global invariant map from H2 with coefficients in the Adels into Q mod Z? It's just the sum of the local invariants. Okay. So that's it. That's the Albert Brouwer-Hasse-Noether theorem, which gives this amazing short exact sequence for the Brouwer group of a global field. Okay, and so again, this is going to be useful for class field theory proper, which occurs in the next lecture, but it's also really cool in its own right. Okay, and so again, this is a long lecture. As I said, I want to give you an application of this short exact sequence. So the application is to Hilbert symbols. So we defined these before. You should go back and look at them if you want to. So in any field, which not a local field or a global field, any field at all that has a primitive nth root of unity, we chose a primitive nth root of unity, and in particular, that a choice of a primitive nth root of unity evidently gives you an isomorphism from mu n of k into 1 over n z mod z. You just send your primitive nth root of unity to zeta n and send the powers to the multiples. This also allows us to define Hilbert symbols. But okay, so just to set things up correctly, I can identify the n torsion in the Brouwer group of every completion with mu n of k if I want to, because the invariant map is identifying the n torsion of the Brouwer group with a certain subgroup. Okay, if KV is non-Archimedean, then this is an isomorphism. If KV is a real place, then this map is not, it only hits the 2 torsion, whatever, that's fine. Anyway, so using the local invariant maps and then just using this isomorphism, I would like things to come out multiplicatively. So I'd like this thing to land in the nth root of unity. So all I'm saying is that you can identify, I just showed you how, the n torsion in the Brouwer group of a local field with, okay, if it's actually non-Archimedean, then the n torsion, this gives you an isomorphism from the n torsion of the Brouwer group into the nth roots of unity. If V is a complex place, this is trivial. If V is a real place, then you're mapping it into plus or minus 1 inside the nth roots of unity if n is even. Okay. So using this, I want to define my normalization of my norm residue symbol. So again, globally, for any pair of elements in K star, by doing a little Kummer theory thing. So the Kummer theory is telling me that if I have the nth roots of unity, then from an nth power class, I can construct a character, and then I do a cup product. I won't review that, but we got a Hilbert symbol, a norm residue symbol, which lands in the n torsion of the Brouwer group of n. Okay. Right. And now I just want the look. So by AB sub V, I'm going to assume that n is fixed. I'm going to take that out of the notation. And so what is AB sub V? Well, basically, this is a class in the Brouwer group of the global field, so I can look at its restriction to the class of the Brouwer group of the local field. But again, I just want it to come out in the nth roots of unity. Okay, and so I arranged for that via the isomorphism. So ABV is going to be an nth root of unity. In particular, I'm about to take n equals 2 for the application that I have in mind. So these local Hilbert symbols are just going to be plus or minus 1, as is the usual definition. Okay. Mostly all I'm doing is I'm just getting something which is multiplicative rather than additive. That's really all I'm doing. And so here's the theorem. The theorem is Hilbert reciprocity, which says that if you normalize these things this way, oh dear, I did it all so that I should be a product on a sub. Okay. That was the whole point. So if you take any fixed A and B and you take the product over all these, again, all but finite, because a global Brouwer class is trivial at all but finitely many places, that was part of what we just did. All but finitely many of these local symbols are going to be equal to 1. And then again, all I did was do an additive to multiplicative isomorphism, basically. And so the reciprocity law, which is that the sum of the local invariance is equal to 0. Once I stick everything in UN, I get that the product of the local Hilbert symbols is equal to 1. Okay. But that's a real reciprocity law. This is actually quite a deep reciprocity law, that the product of the for any, and again, as long as you have an nth root of unity in the ground field, you can do this, and you get that the product of the Hilbert symbols. Okay, so now I'm going to take n equals 2. So 2 is pretty good. I definitely have a primitive square root of unity as long as the field has characteristic different from 2. But I'm going to specialize even more, and I'm going to take k equals q. And then these Hilbert symbols are very, very familiar. Okay. Go so far as to say, if you've never seen these types of local Hilbert symbols, you should look them up somewhere. So I mean, I've given you a definition. The definition is a bit fancy. So for any 2 non-zero rational numbers, and then the places here are just the prime numbers together with infinity. And so I'm associated a sign plus or minus 1 to each one of these. And then you can explicitly compute these things. So this is an exercise in Harari. But so for instance, Sayre's course in arithmetic has a very beautiful treatment of these local symbols. Okay, so there really are, there's just a formula in every single case, depending, it's bimultiplicative. So you kind of want to know, anyway, whatever, you do it out. Okay. What is the content here? The content is figuring out which elements are norms from which quadratic extensions of local fields. That's basically the content here. So you can do that. Okay, so in particular, let's take distinct odd primes. Who knows why? And then I'm going to tell you some of these calculations. So epsilon of x for an odd integer is going to be x minus 1 mod 2. Okay. So I guess 0 if it's 1 mod 4 and 1 if it's 3 mod 4. So for any odd prime, which is different from P and Q, it follows from the complete computation of local Hilbert symbols that the Hilbert symbol at the prime L, which is not 2 and has nothing to do with P or Q, is equal to 1. The case of 2 is more complicated. So the two-adic Hilbert symbol is minus 1 to epsilon of P times epsilon over Q. So that's minus 1 to the P minus 1 over 2 times Q minus 1 over 2. That kind of sounds familiar. What if it's more interesting to evaluate the Hilbert symbols, at the primes that appear? So it turns out that, again, this has to do with things being squares from quadratic extensions. So whether or not they're squares in the residue field is definitely relevant to whether, anyway. So P on Q, local symbol at P, turns out to be the Legendre symbol, Q on P. And in general, the Hilbert symbol is skew symmetric. The B comma A is A comma B inverse, but when n is equal to 2, these are two torsion elements in the Bauer group, so they're self-inverse. Okay, so therefore the PQ at Q is the same as, it's the inverse, but it's an element of order 2, so it's the same as Q on PQ. We just did that one, so it's P on Q. All right, and so now you say, all right, okay, whatever. But the question is, what is Hilbert's reciprocity law telling us? Well, you write it out. And you get that 1 is equal to the product over all these local symbols. Well, most of them were 1 anyway. Which are the ones that might not be 1? It might not be 1 at 2, at P, and at Q. Everywhere else it's 1. Well, at 2 it was this. At P it was, or maybe at Q. Maybe I switched them around. I think it goes that way. Not that it matters because multiplication is commutative. Okay, and so we get. So we get 1 is equal to this, and this is manifestly the quadratic reciprocity law. Okay, bring the minus 1 to the other side if you like. Okay, so that's the point. The point is that this, what did I do? I took this reciprocity law and I just made it more concrete and more concrete and more concrete. And then finally, I took the simplest case that I possibly could, which is that n equals 2 in the rational numbers. And in that case alone, the fact that if you, in order to come from a global Brouwer element, the sum of the invariants has to be equal to 0 is on the nose equivalent to the quadratic reciprocity law. So that's pretty exciting. Therefore, one could view just the fact that the sum of the mod 2 Hilbert symbols is equal to 1 in any global field of characteristic different from 2, you can view that as being a version of quadratic reciprocity in an arbitrary global field of characteristic different from 2. To test how much you like that, here's another exercise. There is another nice quadratic reciprocity law in a rational function field over an odd finite field. So yeah, I have a paper with Adrian Brunyet where we give a new proof of this Dedekind-Arden quadratic reciprocity in rational function fields. So see if you can deduce that from Hilbert's reciprocity law. I'm almost sure that you can. Okay, and then from these results, I won't write it out as completely as other people do, but you do know what the Brouwer kernel is in any finite degree extension of global fields because the global Brouwer group injects into the direct sums of the local Brouwer groups. And so if you have a global Brouwer group element, it's non-zero at some finite number of places. And then what do you need to do? You just, I guess maybe I will say it. So what you need is that if you have a global Brouwer group element, there's finitely many places where it's non-zero. you look at the order of the Brouwer group element in each one of those finite number of places. Okay, so let's call that NV. And then what do you need to do? You need to split it. You need, let's say, to split it by a Galois extension to make things simple. You just need to find your Galois extension so that the decomposition group at V has size divisible by the local order at the Brouwer group NV for each one of those V's. And then by what we already said about the local Brouwer group, that will kill the Brouwer group element. Okay, and so if you work that out, you can show that every element of the Brouwer group of a global field has period equal to its index. Okay, so in other words, if it has order n, then it is split by a degree n field extension. Okay, and that the algebra is cyclic. Okay? In other words, not only does it have a cyclic splitting field, we proved that already, it has a cyclic splitting field of degree equal to the square root of the dimension of the division algebra. And I'll just give you one exercise here. So why don't you try to show that every non-trivial element of the 2 torsion of the Brouwer group of a global field, you can assume the characteristic is not 2 if you like, is split by a separable quadratic extension of the field. Okay, and therefore is represented by a quaternion algebra. Okay, so that was a very long lecture, but now we have the global reciprocity law, and so yeah, I don't know what's going to happen in the next lecture. We have chapter 15 to try to get through in one lecture, so we'll see. All right, any questions?
You mentioned this paper with the alternative proof of quadratic reciprocity and odd characteristic. Any like short statement on what the tools you use are, if not the stuff?
Yeah, so there's this amazing proof due to Zolotarev of classical quadratic reciprocity, which proceeds as its jumping off point that oh dear, what is it? That if you take an element A in FP star, where P is an odd prime, and you look at multiplication by A as a permutation of FP, then the sign of the permutation is the Legendre symbol A on P. So that's very easy to prove if you stop and think about it. So in other words, Zolotarev gives an interpretation of Legendre symbols in terms of signs of permutations, and thereby he also gives a proof of quadratic reciprocity by matching up signs of permutations in some very clever way. And so Adrian and I do adapt his argument to the case of a rational function field. Yeah. And I mean, we sort of have in my own not that successful way, I have this like general setup where if you have a Dedekind domain with finite quotients, you can try to set up a Zolotarev style reciprocity law kind of abstractly. And so there's 3 steps of Zolotarev's argument, and the first 2 steps go through in all kinds of generality. And then of course the 3rd step is where all the magic happens. And so we were able to adapt that third step also in the case of a rational function. Anyway. Okay, yeah, any other questions? Yeah, there's only one paper with me and Adrian and Brevik.
It's one of the cards, right? Zolotarev's paper.
What's that?
It's one of the cards.
Cards?
Yeah, that's what I found.
Okay.
Yeah, where they describe the proof of quadratic reciprocity with cards.
Oh, Matt Baker does this. Yeah, he has like a blog post or something, or some kind of paper, yeah, where he gives a magical proof of quadratic reciprocity, where he literally explains the Zolotarev permutation. It's like you have PQ cards, you deal them out in a P by Q rectangular array, but you deal them out in rows and you pick them up in columns. And that's already confusing, by the way. If you think that, like, if you're not confused, then I mean, I said what I said, but like picture it, you know?
Yeah.
So that permutation that goes from dealing them out in rows to picking them up in columns, you know, it's the composition of two permutations that each sound reasonable. That is the Latarev's permutation. Yeah. And so by the way, yes, I was inspired to do this paper because I read this amazing exposition of Matt Baker, and I was just like, wow, it's the greatest thing ever. Yeah. All right, but yeah, so anyway, at least you should look up what the statement of quadratic reciprocity is in the function field case. But yeah, I mean, I don't remember having done this exercise recently, but it must be true. Anyway, yeah, I'm sure it's true. Okay, well, I think we're done. So see you on Wednesday.